So what we'll do today is we're going to talk about our beams. We talked about them in terms of the equilibrium problems. And as much fun as we like doing equilibrium problems, doing free body diagrams and equilibrium, which is pretty easy. Sum of forces y and moments are pretty easy, but it just gets laborious. And as folks noted, maybe I could start at the other end and make it easier and stuff like that. The more common way we're going to do it is via using integrals and differentials. And what we're going to do is look at these relationships. We're going to set up these relationships and then see how we can go about constructing shear and moment diagrams just using the knowledge of integration and differentials. So we're going to revisit calculus. I know you love that sort of thing. But we'll develop it and we'll find out then it's going to actually be a very nice tool So we're going to look at the differential equilibrium equations for beams. My red go. So we're going to consider looking at a beam here with some arbitrary loading on it. Put our dimensions there, that sort of thing. And what we're going to do now is look at a differential element out of that. So we're going to just take a little piece. We're going to take a little delta x piece out of that. Now, again, we're talking equilibrium here, so that piece has to be in equilibrium. It's not going anywhere. We're going to expose external, internal forces and that sort of thing. But again, we can do equilibrium on that, straightforward. And again, note it's a differential piece, so it's going to be really small. And we know when we cut that side, we're going to expose a moment and a shear. And we'll draw them in their positive convention for the time being. But the other thing we've got on this is there's going to be a little bit of load. So we're going to consider that now. Yeah. So it's just this little bit of load here that we're taking that out and we're bringing the load along with it, whatever happens to be there. And we'll note then that in terms of what we're going to have here, is because now that we've included this little bit of load, in order for that to be in equilibrium, shear can't be exactly equal to the shear here. There's going to be a little bit of change there. And then the moment's going to have a little bit of change also. OK, so now we'll just simply go through and do our two-dimensional equilibrium like we normally do. Oops, I'm in red. First of all, we'll just consider the shear component. Set up our expression. What we'll see is we got V acting in a positive sense. Our other shear on the other side now is going to have that little bit of delta V going on there. And then finally, we've got that little bit of load that we've taken along with us there. Can you see over there? OK. Now, noting that those will drop out, we can set up an equation like that. It's supposed to be an equal sign. Now, what we can do is what those famous mathematicians, the Eagles, did, was we can take that to the limit. So we take that whole term, and we're just going to take it to the limit. And what we'll find then is an expression in terms of a differential like so. Now, anyone know what this means? Don't start singing. Yeah, I got it stuck in your head now. I should have brought the music along with me. I could have stuck it on my phone. Okay, this is basically the slope of our shear diagram. It's dv dx, so it's basically the slope of shear along that x direction there, and it says it's just simply going to be equal to that distributed load at point x. So to state that, the slope of the shear diagram at point x So it's just simply saying that if I can figure out what that little squiggly line is in terms of at any point, what I can do is describe my shear diagram, the slope of my shear diagram at that very point.
What's the significance of the negative sign?
That's thanks to civil engineering, because all loads act down. It's just direction, yeah, yeah. And mechanical engineers always cringe at this because it should be up, but civil engineering, the loads are always down that we worry about in terms of beams and stuff, so. But that's an important point to remember, because a lot of people will forget that. And when we do the next differential, signs will swap on us. Now, the other thing we can do with this is basically we can move the dx over to the other side. So just multiply through by dx. But note then I can do an integration on this from a to b. And when I work through the integration, what we're saying then is that I can measure the change of shear from point A to point B by doing this integration. Does this integration look familiar?
It looks like the work function.
Kind of like the work function. Remember when we did equivalent loads under a distributed load?
Yeah.
So basically that's just simply the area under the load curve. So what we're saying then at this point is then the change in shear from point A to B is just simply the area under that curve. But remember, it does have that negative sign, so don't forget that. But again, recall when we were doing equivalent loads. Remember, we did the distributed loads on the beams. We did the fluid loads, which we converted into a distributed load, basically. All we were doing is just simply integrating that area. We were just calculating the area under the load curve. So we'll take a look at our handouts and then just kind of look at what all of this describes. Jeez, I wish we had one of these on the side here. Okay, so basically this is just simply taking a look at some simple things that were common and that sort of thing. But again, what we just described then is that the slope, question?
For R, is it supposed to be negative integral or is it positive?
It's positive for that, but then again, we assign the direction, remember? So if W is acting down, we always use the R pointing down.
Gotcha.
Yeah. Good question, though. Keep those signs in mind, because that's the thing that catches everybody. So what we just got done describing then is then the slope. So if we have a distributed load on our beam, wiggly however it may be, if I can calculate what that distributed load is at point A, then I can come over to my shear diagram, and my slope at that point will be a minus WA. So again, it's minus, so it should be going down. In other common cases, points where we didn't have any distributed load, the distributed load disappears. We go across there, maybe there's a concentrated load somewhere. As we move across there, note that WA is equal to 0. There's no load, so that implies my slope is equal to 0, which is what we kind of saw when we were doing that equilibrium approach there, that shear basically stayed the same. And you think about it in terms of vertical equilibrium. If we're moving along here and there's no load accumulating, then our shear is not going to maintain equilibrium. The shear doesn't need to change. It's going to be that same vertical equilibrium there, so our slope is equal to 0 at that point. Another common one is a constant load there, or a uniform load basically applied to that. And what we'll see then is the slope on my shear diagram then implies should be constant, but it's now going to be a linear in a negative sense there. If it's going that way, if the load's acting the other way, then it will act the other way. And then the other final piece that we don't have on here, but if the uniform load is triangular or a linear type thing, well then my, my slope will become parabolic. Okay, so what this differential tells me now is what's going on. We talked about how to get the shear from point A to point B. Well, that's two endpoints. What this differential has given me is the information on what's going on between those 2 points. So our next step is we're going to take a look at how to calculate those endpoints. But once we get those endpoints, we need to figure out, OK, what's going on in between it. And this is where we take a look at this information. So going on to the next piece there, the integral, as we just described there, is just simply the area under that curve, including the smudge. But we go from A to B. If we can calculate that area, we might have to do some integration or something like that. But if we can calculate that area, then what we've described is point A and point B. We've described how the shear has changed from point A to point B. And one note to be careful of, and we saw that when we were even doing the equilibrium approach there, when we get under a concentrated load, because basically that has no dimension, basically we can't do that. So we have to slip from side to side there. So we look at, that's why I'm always using the 10 plus and the 10 minus and that sort of thing. So we go a little short of it, go past that, and then continue our calculations there. So it's not valid under a concentrated load. Got some overhead gymnastics we're going to be doing here. Okay, so that's shear. Let's look at our moment. And I won't redraw the picture there, but again, what we're going to be doing is considering our moment diagram there. And what I'll go ahead and put it up. We're going to be taking it from that right face there. Okay, so we're going to take it from this face here. So we're going to eliminate that v plus delta v there. But we'll start considering picking up our terms there. First of all, we'll start off with that couple from that cut end on the other side there, the left end. We've also got the concentrated couple there, the moment on the right side, which is now m plus delta m. Now we'll consider our distributed load there. In the distributed load, the resultant of the distributed load, the force, is going to be Wx times delta x. Delta x is small, but it's still going to be our way of we're basically summing up that area there. That's our equivalent load. And the moment arm is going to be half that distance. Delta x over 2. And then the final piece of the puzzle is the shear on the other end there. Is the v, and it's delta x away from that face. So again, we see some things nicely cancel out. And just dividing through by delta x, basically, we end up with an expression like that. Now again, going back to our mathematicians there, the eagles, we're going to take it to the limit one more time. And note that this will be the slope of my moment diagram. And we wonder what's going on with this part here. Well, my delta x is on top in this one. And since I'm forcing delta x in the limit to go to 0, that term disappears. So what we see is a very similar thing, although now it's a positive sign. There's no negative sign there. So what that's telling me is the slope of the moment diagram at point x is simply equal to the shear value at x. And some of you were recognizing that when we were doing the equilibrium approach. Okay, so again, what we'll do is multiply through by dx there, move the dx's, get all of our x's on the one side there. And then we're going to do the same integration from point A to point B. And what we'll find then is then the change in moment from point A to point B is just simply going to be the area under that shear diagram. So it's a little bit different. We're now looking at shear, but again, it's very similar to what we did with the load and creating an equivalent load and that sort of thing. Just go calculate that area. One note here. You have to be a little careful here because we have to make sure we keep track of positive and negative areas there. So a lot of times we see shear, remember, going through zero at places. We saw that example there on last Thursday there when we were looking at the equilibrium method there. We have to be careful that we can't just simply do this whole area. We've got to do the area positive, and then the area negative, we subtract from it. We'll be basically taking it down. So again, take a look at what the differential and the integrals are telling us in our sheet.
What's omega x?
Omega x is that distributed load. So if it's like constant, it'll be 5, and if it's linear, then it'll vary from something to something.
So load below the x-axis for negative area, you have to take two integrals?
Beg your pardon now? What was the question?
Oh.
So.
Do you have to take two separate integrals for that then? Or if you have negative area as well?
Yes, yes, that's the key thing, and we'll see that in the example, is that it's not necessarily, what we're going to find is that we're not going to force ourselves to do calculus. We're going to be able to do rectangular areas and triangular areas and that sort of thing rather simply. Only run into problem when we get into quadratics and cubics and stuff like that, where you have to do a little bit of integration and stuff. But yes, you would have to do a positive area and a negative area, and we'll see that in the example. Sir?
We put in linear quadratics on the example.
Oh, of course. Yeah, we're going to make it hard somewhere.
Give me extra those papers too.
Yeah. Okay, so right in front of so again, what the differential approach is telling us is that there's smudges on my overheads. But again, as we described, dm dx is equal to the shear at that value. So if I've got a shear diagram that's going all over the place and that sort of thing, the key thing is if I can calculate that value at A, then I have the slope of my moment diagram at A. And in this case, note that if it's positive value here, it will be a positive slope. And then other common cases that we run into is the one that we kind of talked about in the equilibrium case there, where the shear goes through 0 or happens to be 0. What that tells me then is that the slope of the moment diagram is equal to 0, which means that it's flat, basically, and I've either reached some sort of a max min saddle, or maybe just a constant place where moment is constant. But basically, it tells me that my slope is 0, and if it's at one point, it'll be at that one point. If it's across the whole thing, it'll be across the whole thing. If I have a constant shear, which is a common case there, what that's telling me is then my slope of my moment diagram is constant, which means then it's going to be the same no matter what I look at it. If this is a value of 5, it'll be 5. The slope will be 5, which implies then I have a linear moment diagram, and it'll be constant through that length from A to B. And then the more common case that we run into is when we have a linear shear, where the shear is changing linearly. When does shear change linearly? Distributed constant load, uniform load. OK. When we have a uniform load, we should expect to see a linear shear. Oftentimes, it will go through 0. But the key thing is then my moment diagram then is parabolic. And again, what we're using this information for is we can calculate the moment at A, we can calculate the moment at B. What we need to know is, OK, what's going on in between? So any of these can have 2 different values there, but it might be parabolic between them, it might be linear between them, we don't know. Then finally, the integration. It's similar to what we did with load, except now we're looking at the shear diagram. Now that's a key thing. When we do this portion of the moment diagram, we have to have a shear diagram. So we have to calculate the shear diagram first. So it is a bit sequential. And as we work our way across the beam, we'll see it's a sequential approach. It's very similar to a method of joints and that sort of thing, where you start somewhere and you just kind of work your way across. So we can't do anything until we have a shear diagram. Once we have that, though, we can calculate that area underneath there, and then calculate what happens from moment point A to moment at point B. And again, that's endpoints. We have to go back to the slope thing to tell me what's going on in between. Moment equations happen to be valid under concentrated loads. And again, we saw that with the equilibrium approach. When we went past that concentrated load, yeah, it's going to participate in the moment equation, but if the moment arm's 0 to start off with, it's not going to participate until we get some distance away from it. So that's kind of consistent with what we saw there in the equilibrium approach. The one problem that we do have is if we have a concentrated couple, then we have to treat it like we did with a concentrated force and shear. Look at one side and then jump over to the other side. Yes, we're going to do the same example we did in the equilibrium approach. Just a few more notes here, and then we'll get started on that example. And this is for those of you who love math. You're all engineers. You got to love math. You have to admit, though, this is relatively simple math. So it's just simply slopes and doing some simple integrations and stuff. OK, recall that we'd set our relationship there of moment and shear. I can take the derivative of that one more time. And note that if I take the derivative, then the second derivative of the moment basically is related to the slope of the shear diagram, which is then related to my load there. The main use for this really is So if we want to go through and do the equilibrium approach and want to do this differential, we do it twice. If it comes out as a negative value, then it just simply implies that my moment diagram now is going to be a concave down. And if we look at it, if it comes out positive, then it's concave up. So it just kind of gives us some clues, but there's some easier ways of doing that. But again, if you like math, that's
Does that like if the slope is negative, when would it be concave down?
if we go through this calculation, we have the moment equation in terms of x. If we do the differential twice and the value of that comes out as negative across that span, then that implies then that my moment diagram should look like this. It should be curved like this.
I mean, that would be the moment diagram, but for the shear diagram, would it be like a negative? Because you know how it's linear on the shear diagram. It's parabolic on the moment. So if it's concave down, would that mean that it was a negative slope on the shear diagram? Or not?
Yeah, that's a good point, yeah. So you'd see that sort of moment diagram with the shear doing this way. If the shear is going the other way, then it'll look like that.
Okay. I think the first derivative gave us the slope, and the second derivative gave us the concavity. Are we taking the second derivative?
If you want. This is basically, what we're going to find is a much easier way of looking at it. But those that like math and that sort of thing, you can look at it. It just shows you that there is a relationship all the way through. What we're going to do is we're going to take a look at now the problem that we started, or that we actually did with the equilibrium approach. We're going to look at it now using this differential approach and hopefully see that it's a little bit easier, but it's a little bit harder in the sense that you have to be careful. It's so sequential that if you make a mistake along the way, you can find yourself in a real mess. But again, we're going to go back to this problem. If you've got it, hopefully pull it out and take a look at it. But again, distributed load over a portion of it. We've got a concentrated load. We've got a concentrated couple. And then we've got the two end forces, which are concentrated loads. And we have to pay attention to those. OK, what we're going to do is we're going to set up the diagrams. And when you set it up in your notes, what I want you to do is set maybe a half a page or something. What we're going to do is we're going to keep coming back to it. So we're going to keep this diagram, and we're going to kind of work our way across it. So set it up. What we're going to do is our typical diagram, free body diagram. Shear, and then moment. And again, even like we did in the equilibrium method, when you set up your free body diagram, we're going to look at that because we're going to have to break it up at those points where load changes. So we're going to keep that portion and keep coming back to that. Now, part of what we're going to have to do is when we talk about these portions where there's concentrated loads and concentrated twists and that sort of thing, because the shear diagram is so sensitive to that, we're going to have to look at some infinitesimal small pieces to see what's going on and apply equilibrium to them. So when I consider that infinitesimal piece there, A, what I do is I put in my positive convention for moment and shear, and then I've got this concentrated load. Of 17.5 kips. Now, yes, there's some distributed load going on there, but again, as we take this smaller and smaller, it's not going to participate. In considering equilibrium, if I do the sum of forces in the y direction there, my shear and my 17.5 have to equal each other. So what that's telling me then is for this infinitesimally small piece at A, my shear diagram makes a jump of 17.5. So I don't start at 0. It's starting as a positive 17.5. When I consider the moment, again, since that's so small, that delta x is almost 0 there, there's no moment, basically. So I come back to my moment diagram, and my starting point for my moment is at 0. So that's a little bit of equilibrium we have to do in terms of the case. And again, now what we'll look is between that section A and B there, and again, just slightly on either side because I do have a concentrated load there at B.
That first one was just A, right? The first piece?
Yeah, A plus. So it's an A and a tiny little bit. Yeah. And now we're going from A plus now to just short of B.
Moment is 0 at B. I mean, 0 because there's nothing else acting on it.
Moment, yeah. When you think about it, this is so small. The moment arm's so small. The only thing is here is this 17.5. But when I'm right up at, I'm on top of it essentially, it's equal to 0. So it's starting off at 0. It'll change as we go along there. So this is my free body diagram. But let's consider what I want to do is my integral approach. And I'll show it as an integral, but again, what we're going to find is that we can just simply do simple shapes. So just setting up the integration, I move the VA over to the other side there because I'm interested in solving for VB minus, essentially. OK, but the key thing I wanted to bring there is that notice that I started off at VA plus at 17.5. And then it's also going to then be equal to the area under that load curve. This is a nice linear uniform one, so it's going to be equal to that area, which is 2 and I just simply multiply the 2 times the 10. So a nice simple integration. I don't have to worry about doing the integration. I just calculate that area. So that's telling me then at point B, my shear drops down to 2.5. Now, this is where I go back to my differentials and I say, OK, what's going on in between? Well, let's take a look at my differential. dV dx is going to be equal to that uniform load across there, right?
What about the 10 kips going?
I'm just short of that. That's why I go B minus. Yeah, good thinking, though. Yeah, that's going to surprise us. OK, so my shear, dV dx, is equal to a -2 across that whole length there, which then basically says I have a linear distribution like that. Now, the important thing is note, Ben, we've got that issue that we talked about where we went through 0 there. So we're going to have to be careful when we get into our moment diagram. In terms of my moment diagram, what I need to do is I want this area. And then I want that little negative area there. So I've got some triangles here to deal with.
Where it goes for 0, is that an absolute max?
It will be a max, yes. And in this particular case, yes, it'll be absolute. But you've got to be careful. You can't assume it. It's just saying that the moment goes to 0. So it might be a maximum. It might be a
Yeah, depending on the slope.
Yeah. But depending on the loads on it, it could wave and go up even higher and stuff too. So you got to be a little careful with that.
Okay.
As a matter of fact, well, we'll see that when we get to the concentrated force or concentrated couple.
So now is there just a step continuity up to the 10 kips?
Yes, we'll see that when we do the little equilibrium. Let's finish this portion first. OK, the first thing we have to do here is note that this distance, we do similar triangles. So basically, I've got to figure out the length of this triangle if I'm going to calculate its area. So we have the 20 over 10, so 17.5 plus the 2.5, which would be this triangle here, the big triangle, is going to be similar to that x star, right? So we can do just similar triangles. And we find then that x star, which is what we found in that equilibrium approach too. But we did that a little differently there. We went and found where the moment or the shear went equal to 0 there. Sir.
20 over 10 come from again?
This leg is 20 of the whole triangle, right? All the way down to the -2.5 across the 10. That's a good question. I want to make sure everybody's clear on that. So that's the big triangle. What I'm interested in is the little triangle now with the shorter leg of 17.5. And where does that x end up? And we find that it ends up at 8.75. Now I need that because now the next thing I'm going to do is my moment. And the expression for that n, again, is the area under that curve. But that area is going to be a little bit easier now. Moment at A is equal to 0. And the area under that triangle now is going to be 17.5, which is my base leg there. And then it goes over to the 8.75. And we'll find that that was that same value that we saw when we did the equilibrium approach. So it's topped out there. That's the highest it's going to get. And it happens to be the absolute in this particular case, but not always. But it will be a maximum, because then when I consider what's going on at B, what my expression looks like now is I'm going to go from the x star to the b, but that's going to be a negative value now. And note then the area of that triangle, which is a bit smaller, the leg is 2.5. The base now will be the 10 minus the 8.75, or 1.25. Multiply that, but it's now negative because it's on the other side of the curve there. So I'm going to be subtracting that off. And what we find is we end up with that same endpoint. So what that's telling me then is under this point now, I define 2 points now on my moment curve there. I've got a high point there of 76.56, directly under that place where the shear goes to 0. And again, as you should always look for those maximums under shear equal to 0. And then it drops down to 75. Now, what goes on in between? Is it linear?
Parabolic.
Parabolic. Curve up or curve down? Concave down. Another way to think about it is again, if it's equal to the slope, right? The moment curve is going to be equal to the slope. Well, look at how big my shear is at this point. So what I'm going to see is a big slope here. When I get to this point, my slope is 0. And when I get to this, I got a little negative going on. So just kind of fitting those slopes in there. Think about it that way. Again, slope of the moment diagram is equal to the shear at a point. So what we're going to see is then it's going to start off big, and then it's going to work its way to a flat, and then start heading down, and end at a slope of minus 2.5. So if you don't want to do the math, just simply go back to that dm dx is equal to v. And just look at various points there, big, littler, 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 0, negative. OK, now we've got that messy point. Let's think about what's going on at B minus and B plus there, basically point B. My free body diagram, now I've just solved for the shear and the moment on that side. So my shear I solved as 2.5, so I'm going to draw it in the negative direction now. Right? Positive convention was up on that side, but I solved it as negative. And then my moment was 75. And then the one piece that's missing is that 10 kip load there. And then this is my unknown shear and moment at B plus. So that's really at B plus. So when I get done with that quick little infinitesimal piece there at B, and I walk across that, that's where I see that jump that we saw in the equilibrium approach.
Just to clarify, you put it at 2.5 down just because it's negative, right?
Because I solved it as negative, yeah, over here. You can put it arrow up and put a minus 2.5 if you want to do it that way too, whatever you're comfortable with. Yeah. That side's known, so I can go ahead and put in the signs the way I want them. The other side I'm drawing as in their positive convention, and I'll let things solve. And as a matter of fact, my shear solved at 12.5. So what I see now, and got my moment diagram and my shear diagrams coming together here. We're going to see that vertical drop of 10 like we saw in the equilibrium approach there. So again, just to let you know, you don't necessarily have to work through the equilibrium approach, but I'm wanting you to see how we walk through it. Question?
I might have missed because I was writing down, but why do you have 10 over
That's the value. Oh, I'm sorry. No, that's supposed to be minus 2.5. Sorry about that. Good point. Too many 10s on the head. So that's this piece. We pick up the 10, that's negative. And then the shear, the positive convention for this side is shown as a negative. We solve it. Basically, we find it as a negative value. And what we see then is what we saw in that equilibrium approach there is a drop of 10 at that point B due to that concentrated load. So that's how we treat concentrated loads. We can't integrate under them, but we just do a little equilibrium approach there. Moment. And what we'll find is then the moments equal to each other again because that 10 kip load has no moment arm at this point in time. So it doesn't change, basically. And we saw that in the equilibrium approach when we were looking at concentrated loads. Since the moment arms are 0, basically they're not going to, well, the moment will start picking that up as we start moving away from it. OK, so now we'll continue our march across here. So that's A, B, C, and D. And we're going to, again, cut short of that concentrated twist there because the moment diagram doesn't particularly like that. But again, my equation looks like that. But when we go over here and look, we notice that there's no load being applied here. There's no distributed load. We've gone past the concentrated load. So between B and C, this portion does nothing. And what we find then is that my shear at this point is going to be that same minus 12.5. And again, appealing to, OK, what's going on in between? dv dx, in this particular case, if there's no load going on, because dv dx is equal to a minus omega, basically that's saying then it's going to be constant across the bottom there. It'll be a minus 12.5 from B to C. Let's go. Moment's not going to be so easy. Or is it? So my moment diagram, again, I need to start off with my moment at the point B there, which was 75. And then I need to figure out what that area is under the load curve. No, under the shear curve. Yeah, thank you. Good point, though. Yes, we're looking at moment now, so I need to look at the shear curve. And that's why I said we got to get the shear curve done first. Well, that's going to be nice and easy. We got a rectangular area, 12.5 across 5. And it turned out to be 12.5 feet. But again, that's my end point. Now, the nice thing about this one is now the shear curve did not go through 0. So I don't have to worry about positive and negative areas there and stuff like that. What goes on in between, again, think about my moment is going to be equal to that shear. Well, it's going to be constant, which then implies that I'm going to have a constant negative slope of 12.5. So the 12.5s are not magical. That just happened to come out to that number. But the slope is going to be equal to and it's linear in between. And again, how we deal with the next piece, we're just going to do a little equilibrium piece around C. I need to change some of these values now. Okay, so what my little equilibrium piece looks like, again, get my left side correct there. My shear is now jumped down to 12.5. It's not the 2.5 anymore. And my moment happens to be a positive 12.5, but that's in kip feet. And then I apply that concentrated couple to 50 kip feet in a clockwise direction there. And what we'll see is then shear doesn't change there because it's a concentrated couple. So in terms of vertical equilibrium, nothing's going on there. It doesn't see any change there. So my shear is not going to change as I go from point C minus to point C plus on the other side of that concentrated couple. My moment, however, what we're going to see is this concentrated twist now jumping in. And again, that's that free vector we talked about. Remember that free leaf vector? It just pops into the equation there. So I put in my C minus portion there, which was 12.5 there, the 50. And I think that was come out right. And what we'll see then is a jump in my moment diagram. So the shear diagram doesn't jump. The moment diagram now will see a jump, like we saw in that equilibrium approach there. Yeah, I'm trying to think. Did I do that?
Minus 15, not plus 15.
Yeah. Need to fix it in my notes. Take off some points. So then we'll finally look at our last piece there. And again, the equation looks like that. There is no load acting in that portion there again. We've jumped past that concentrated twist. Question?
Why does the shear go downwards on both sides of the SPD?
Well, this one's acting. This is negative. We solved that earlier, right? As minus 12.5. When we said we did piece B plus to C minus. So go back there. That came out as a minus 12.5. This is the positive convention for this cut, right? So I always put it in the positive convention. When I solve for that, well, they're both negative. They're both going in the right that direction there, which implies then that it has to flip sign, which means then I solve it as minus 12.5 to keep that in equilibrium. That one has to flip, right? And the way it flips is we put a minus sign in front of it. Okay? So this one I know is acting that way. This one, I just put in the positive convention. It's solved as negative, so it says it's got to flip to keep that in equilibrium. Does that make sense? Okay. So this piece goes to 0. Which says then if I work my way across here, that's going to be minus 12.5 also. And again, since there's no load there, what that tells me is then my slope will be 0 or flat. And then finally, I need to do my moment curve, and basically that's going to be the area under this shear curve, which is again that same value. So my moment starts off at and then the area under the shear curve is just simply that minus 12.5 times that distance from C to D of 5. And that comes up as 0. So then that tells me my endpoint for my moment diagram will be here. And again, what goes on in between the two? It's a minus 12.5, a constant slope, which then says that I have a slope of 12.5 to bring it down to there. Now, again, what you want to do is check yourself, because one of the problems with doing this approach, it's actually easy. You don't necessarily, a lot of people, when you start doing this as engineers and that sort of thing, you do a lot of this in your head. You're not laying it all out like this. But you need to check to make sure at the very end you get what you expect, because it is a sequential method. And if you make a mistake along the way there, it'll be easy to, the error will accumulate. So let's just look at piece D. Oops, got the wrong direction. OK, so this is what I just solved for. I said a moment is equal to 0. And my shear at that is equal to 12.5, and it's acting down. It's negative. So I'm reversing the sign on that. And what we think it's going on at the very end here is going to be this concentrated force of 12.5, or 12.5 acting up. Well, when we think about vertical equilibrium, it's in equilibrium. And then my moment is equal to 0 anyway. So basically, we're saying that. So you want to check yourself. So when you get to the end there, if there's a concentrated twist there, or if there's a concentrated force there, you want to make sure that you actually have that, that value there. So
the V there goes back to.
and then the V, yes, good point. So then V basically goes back up to 0 there. Now, that's a long, laborious way of doing it, but basically that's the thinking that goes behind it. Again, as engineers, you'll start doing a lot of that in your head. And most of you will end up using the differential approach anyway.